Welcome to the First Mold Insights, where we talk about injection molding, rapid tooling, product development, and real-world manufacturing insights. Today's topic is injection molding gate types and placement. Alex, we've talked about sprues and runners before, but the gate really feels like that final critical junction, doesn't it? It's where the molten plastic finally enters the mold's cavity. What makes it such a challenging part of the whole feeding system?
Yeah, Mia, it really is the last checkpoint. The sprue gets the plastic in, the runner distributes it, but the gate is the actual entry point into the part, and that's why its location, its design, it's all exceptionally crucial. Some folks even say the success of a mold design hinges directly on choosing the right gate location. Get that wrong, and you're fighting an uphill battle with part quality, cycle times, you name it.
Interesting. So, it's not just about getting the plastic in there, but how it gets in. From what I understand, gates are generally categorized into two main types, restrictive and non-restrictive. Can you break those down for us?
Right. So, restrictive gates typically refers to sprue gates. They've got a narrow opening that well restricts the flow, synfla, but can be limiting. Then you've got non-restrictive gates, which is a much broader category, offering a lot more design options and flexibility for different part geometries and materials. That's where most of the different types we'll talk about today fall.
Okay, so let's dive into some of those non-restrictive types. What's one of the most straightforward ones you often see on the shop floor?
Well, probably the direct gate or sprue gate. It's often positioned right at the center of the part in a single cavity mold. The plastic melt just flows directly in. It's a short path, fast feeding, generally good molding effect. You get less pressure and heat loss because the cross-sectional area can be pretty large. And for the mold maker, it's a simple structure, lower cost to build.
Sounds ideal, but I'm guessing there's a catch?
There always is, right? The biggest downside is gate removal. It's difficult, and you're almost always left with a visible gate mark, which can really affect the product's aesthetics playas. You get a lot of heat concentration and internal stress around that gate, which can lead to defects like sink marks. And for thin-walled parts, especially with crystalline plastics, you can see deflection. So you typically use direct gates for large, thick-walled parts. Think big pots, TV housing sore for plastics with high viscosity and poor flowability, like PC or PSF.
That makes sense. So, for parts where appearance is critical or they're thinner, you'd need something different. What's another common gate type?
Next up is the edge gate, also called a side gate or rectangular gate. This is super common. It's usually located on the parting surface and feeds from the outside of the cavity. It's small, typically a rectangle, and pretty easy to process.
And the advantages there?
Oh, quite a few sithy cross-section, easy to machine. You've got a lot of flexibility in where you can place it. Gate removal is easier, and it leaves minimal traces compared to a direct gate. You can also play with its dimensions to change the mold filling conditions. It's great for multi-cavity molds and high-volume production. We use them a lot for small and medium-sized plastic parts.
That sounds like a workhorse gate, but I imagine it's not perfect for everything.
No, not quite. Air exhausting can be a challenge, especially for shell-shaped parts. And if you absolutely can't have any feed traces, it might not be the best choice. There's also usually a larger pressure loss during injection compared to a direct gate. Related to the edge gate, there's also the overlap gate. It's a variation, also processed on the parting surface, but it's more prone to sink marks and can be even harder to remove, leaving more noticeable gate marks. We don't see those as often for aesthetic parts.
Okay, so edge gates are versatile. What about something that helps with melt distribution, especially for larger, flatter parts?
For that, you'd often look at a fan gate. Think of it like a folding fan. It widens and gets thinner as it feeds the melt into the cavity, usually through a stepped gate. It's another variation of the side gate. The big advantage here is even melt distribution across the width of the part, which really reduces flow patterns and orientation effects. It also helps improve air exclusion.
So, better for aesthetics and material properties, what kind of parts would you use that for?
Exactly, long, flat, and thin products are ideal things, like cover plates, rulers, trays, or just general flat plates. It's also good for plastics with poor flowability, like PC or PSF, similar to the direct gate, but with better distribution. The downside is it can still be difficult to remove, and you might get some shear marks along the product side.
We've talked about flat and thick parts. What about cylindrical parts? Is there a specialized gate for those?
Absolutely. Where cylindrical parts, especially those with large bores or even large rectangular bores, you'd use a diaphragm gate. The material injects into the cavity from the perimeter of the bore. This is great because it distributes the force evenly on the core, helps avoid weld lines, and facilitates smooth exhaust. The trade-off is that it leaves noticeable gate marks on the inner edge of the part. Then there's the ring gate, which is similar but positioned outside the cavity, wrapping around it. It's another variant of the rectangular gate.
So, a ring gate is essentially an external diaphragm? And what are the benefits of that?
Pretty much, the ring gate also gives you really even melt distribution along the circumference, smooth exhaust, and a flow that's ripple-free and fusion-free. It helps reduce internal stress and deformation, which is fantastic for those long, thin-walled cylindrical parts. The downside is similar to the diaphragm gate, difficult removal and noticeable gate traces on the side, meaning you'll likely need some gate residue removal for aesthetic purposes. We see these in small, multi-cavity molds for cylindrical parts.
It sounds like there's a common theme of balancing melt flow advantages with post-processing challenges. What about very thin, wide parts?
For very thin, wide parts, you might use a film gate. This one uses a parallel runner that's aligned parallel to the side of the cavity, often as long as or even longer than the part's width. The melt is evenly distributed in this runner and then enters the cavity through a thin, flat slit at a uniform speed. It's great for uniform, smooth melt flow, reduced internal stress, and effective gas removal. We use it for thin plate plastic parts, especially those with a large molding area, and it's good for controlling deformation in materials like PE.
Okay, so it sounds like a good choice for delicate flat parts. What's the main challenge with film gates?
Like a few others, it's difficult gate removal, and you can still end up with shear marks. It's always a compromise. Now, moving on to something quite different. We have the pinpoint gate, or just pin gate. This is a very widely used gate type, round in cross-section and quite small, typically 0.6 to 2.8 millimeters in diameter.
Pin gates always sound like they'd be really precise. What's the appeal there?
They offer a lot of location flexibility. They also allow for automatic gate removal, which is a huge plus for automation. You get reduced residual stress at the gate, and it solidifies faster. They're good for multi-cavity center feed molds and for low-viscosity plastics or those sensitive to shear rate.
So, what's the catch with something so flexible and automated?
Well, they have high pressure loss, so you need higher injection pressure. The mold structure is often more complex, usually requiring a 3-plate mold, though you can use them in 2-plate hot runner molds. That high flow rate can cause increased molecular orientation and even potential cracking. And for large or easily deformable plastic parts, they're prone to warpage.
That's a significant list of considerations. Is there a way to get some of the benefits of a pin gate without all the mold complexity?
Good question, actually. That's where the submarine gate, or tunnel gate, comes in. It's an advancement of the pin gate design. It retains the benefits but addresses some of the complexities. The big thing here is its hidden placement. It's often conical, angled between 20 and 40 degrees relative to the cavity, and can be placed on inner surfaces, sides, or even bars or columns. You can even set it up to be sheared off by the ejector rod.
Hidden placement and automatic removal? That sounds like a game changer for aesthetics.
It is. It preserves the product's appearance, and that automatic gate removal really enables production automation. No spray marks or airlines on the surface either. It's great for plastic parts with one-sided feeding and commonly used in 2-plate molds. However, it's harder to process because of that submerged oblique direction. It's also not ideal for thin-walled products due to high pressure loss and easy condensation, and for really strong plastics like PA, cutting the gate can be challenging, while brittle plastics like PES might just break and block the gate.
So, it's a great option, but you really have to consider the material. Any other variations of the side gate we should know about?
Yeah, there's the tab gate. It's an evolution of the side gate, serving as a typical impact gate. The gate itself is usually square or rectangular, and the runner is preferably circular. Its main advantages are smooth, even melt flow into the cavity, and improved melt fluidity because you can increase the temperature in that region. Crucially, residual stress at the gate doesn't tend to affect the molded part quality, and it reduces internal stress in the plastic overall.
Sounds like it helps with material integrity. What are the downsides for the tap gate?
The main ones are difficult gate removal, and it leaves a pretty significant trace palleus. You often end up with a longer, more complicated flow channel.
Okay, Alex, so we've got all these different gate types, each with their own pros and cons, specific applications, and materials they work best with. How do you even begin to choose where to put the gate on a part? What are the key considerations for gate location?
That's the million-dollar question, Mia, and it's where the real experience comes in. There's no fixed right answer, as product structure and material vary wildly, but there are some core requirements. First, you want to minimize visible gate marks and weld lines on the final product. That's a big one for aesthetics. Then you've got to consider the product's functional requirements, ensuring proper filling, packing, and overall performance.
So it's about both look and function?
Exactly. And then there's the mold design and manufacturing ease. You want to make it feasible and not overly complex to build the mold. The gate location should also minimize any potential deflection or distortion during molding, and of course facilitate easy gate removal after molding. Plus, it should allow for easy control of molding process parameters, like melt flow, pressure, and cooling.
That's a lot to balance. Are there any general rules of thumb for where to position it on the part itself?
Oh, definitely. You always want to position the gate to ensure simultaneous filling of all corners of the cavity. The plastic flow rate should be uniform and stable throughout the whole injection process. Crucially, place the gate in the thickest part of the product's wall thickness, allowing the molten plastic to flow from the thick section to the thin section. That really helps with complete mold filling. You also want to minimize the length of the plastic filling process to reduce pressure loss and put the gate in a spot that helps gas escape.
So thick to thin, minimize flow path, and aid gas removal. What else should designers watch out for?
Don't direct the melt straight into the cavity, especially with narrow gates, as that can cause swirling flow and spin marks. You've got to consider all those potential issues like weld marks, bubbles, depressions, insufficient injection, and material spraying. If you can't avoid weld lines, at least place them where they'll have the least impact. For circular parts, add cold material wells at the melt pouring point to prevent weld lines, and generally design the gate to prevent melt fracture. If you have a large, flat part, don't place the gate just on one side. You'll get uneven injection force distribution.
So, avoiding aesthetic and structural weaknesses. What about very specific part features, like thin cores?
Good point. For molds with long and thin cores, the gate should be located far from the core to prevent deformation caused by the material flow. And for really large or flat plastic parts, you can actually use compound gates, multiple gates, basically to prevent deflection, deformation, and material shortage. And like we talked about with some gate types, the design should always facilitate easy water outlet operation, preferably automatically.
That's a comprehensive list of best practices, but even with the best design, things can still go wrong. What are some of the common defects you see related to gates, and how do you fix them?
Yeah, defects happened. One of the most common is a gate vestige or gate mark, basically, a visible leftover from the gate. That's usually caused by a large gate size, improper gate shape, or bad location. The solution is to use a smaller gate, change its shape, or optimize the location to make the mark less visible. Sometimes it's insufficient gate filling, so you adjust injection pressure, speed, or temperature.
What about discoloration or lines around the gate?
That would be gate blush or discoloration. Often it's thermal degradation or insufficient melt temperature. So you'd increase the melt temperature, adjust mold temperature for better heat transfer, or even switch to materials with improved heat stability or use additives. If you see gate shear or flow lines, that's usually poor gate design, insufficient injection speed, or improper mold temperature. Optimize the gate design for smoother flow, increase injection speed, or adjust the mold temperature.
And what if the gate itself isn't working right, like it's blocked?
That's gate freezing or blockage. That's often due to a small gate size or improper design. So increase the gate size, modify the design. It could be process parameters, so optimize injection pressure and temperature. Sometimes you just need materials with better flow properties or additives. Finally, gate burrs are another common one. That's usually improper gate size or shape, inadequate cooling and ejection systems, or poor mold maintenance. The fix is using the right gate size and shape, improving cooling and ejection, and sticking to proper mold maintenance and cleaning practices.
Alex, it's clear there's an incredible amount of nuance and experience that goes into gate design and placement. For all the engineers and product teams listening, what's the one most important takeaway you want them to remember about gates and injection molding?
Look, for mold designers, what often really tests them in injection molding factories is gate placement. Because every client's product, structure, and material vary, there's no fixed correct answer. Sicking gate placement requires a certain level of practical experience.
Thanks for tuning in. For more manufacturing resources or custom part production services, visit firstmold.com. We'll see you next time.